Hello everyone and welcome to this lesson. Today's lesson is intermolecular forces, and the objectives of our lesson today is that at the end of the lesson you should be able to distinguish intermolecular and intramolecular forces, describe the different types of intermolecular forces, explain the effect of different intermolecular forces to the physical properties of substances, and finally use the knowledge of intermolecular forces to predict the physical properties of compounds. Now let us start with the revision exercise. Explain in terms of structure and bonding why silicon dioxide is a hard solid whereas carbon dioxide is a gas at room temperature and pressure. Explain why graphite is a good conductor of electricity while diamond is an insulator. We discussed this last time when we were studying the giant and simple molecular structures. Here you have to stop the video while answering the questions, and you will go on watching the video when you are done. Answers. Silicon dioxide has a very high melting point at room temperature and pressure, whereas carbon dioxide is a gas because silicon dioxide has a giant structure. We have seen that giant structures have so many strong covalent bonds resulting in a three-dimensional structure which need or require a lot of energy to be weakened and melt the substance, while substances like carbon dioxide, which have simple molecular structures, they have weak intermolecular forces which are very easy to weaken and melt the substance. Answer number 2. Graphite has delocalized electrons, as each carbon atom makes 3 bonds only, but in diamond each carbon atom makes 4 bonds, so that there are no free moving electrons. In diamond we have each carbon atom which makes 4 bonds. We have seen that, and we have no delocalized electrons. But for graphite, each carbon makes 3 bonds only, leaving one electron, valence electron, without making a bond, and that one is delocalized. Intermolecular and intramolecular forces. What is the difference, or what is the similarity between intermolecular and intramolecular forces? First of all, let's define intramolecular forces. Intramolecular forces, they are these normal forces we know. You can see here we have intra and molecular. So these are the forces which are found within the molecule. They hold atoms together in a molecule. But here we have intermolecular forces. So this one is a type of forces, attraction forces, holding together molecules in a substance. Intramolecular forces and intermolecular forces compared. Here the intermolecular forces are weaker than intramolecular forces. Intramolecular forces are the forces that hold atoms together within a molecule or a compound. They are known as the normal chemical bonds. The normal chemical bonds we have discussed. Here we have the covalent bonding, the ionic bonding, metallic bonding. Those are intramolecular forces. Intermolecular forces, as I said, they are forces that exist between molecules. They hold molecules together in a compound. When you break molecules, you will have atoms separated. So when you break intramolecular forces, when they are weakened and finally broken, the atoms making the molecule will separate. If we have, for example, carbon, which is connected to oxygen in carbon dioxide, then if you break the intramolecular forces, which are these chemical bonds, then you will have your two oxygen atoms plus one carbon atom. Why? Because you have broken these forces, the chemical bonds which were holding the atoms together in this substance. But what happens when you break intermolecular forces, the forces which hold molecules together in a substance? When you break them, the intermolecular forces, the molecules will be separated, but the atoms within the molecule will stay there. You don't break the molecules, but you separate molecules in the substance. The types we have for intramolecular forces, we said that they are ionic, covalent, and metallic bonding, while for intermolecular forces, we have these main types. We have dipole-dipole forces, we have hydrogen bonding, and van der Waals forces, which are also referred to as dispersion forces, London dispersion forces. Here we have an example showing the intramolecular forces. Here we have the bonding within the molecule. This is the intramolecular force. This is a covalent bond, polar covalent bond. And here we have an example of intramolecular forces, which is the attraction force that holds molecules together. You can see that the dash line here is joining the two water molecules. Let us start with the dipole-dipole interactions, dipole-dipole forces. Dipole-dipole forces, as shown here, can see them here in hydrogen chloride substance. We have the dipole-dipole forces. And how do we define these forces? They are forces which occur when partially positively charged parts of a molecule interact with the partially negatively charged part of the neighboring molecule. Here we have a partial negative pole, that is the chlorine atom with a partial negative charge, and hydrogen with a partial positive charge. So because of being negatively charged and partially positively charged, there is some attraction between the two poles. Here we have a negative pole and a positive pole. You remember the polarity of bonds. The polarity of bonds, because of electronegativity difference, results into the formation of poles in a molecule. So there will be a permanent attraction between the opposite poles of molecules within a given substance, and those attraction forces, they are the ones we call dipole-dipole forces. They occur in polar molecules only, the substances which contain polar covalent bonds, which contain poles. And here we have the example, which is hydrochloric acid or hydrogen chloride, where you have the dipole-dipole forces, the attraction between the negatively charged pole and the positively charged pole. Hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular forces. You should always remember that in intermolecular forces, hydrogen bonding is the strongest, and it is formed between a hydrogen atom, which is already, this is the, here we have the key words for our definition of hydrogen bonding, because sometimes the definition may be confusing, but here you have to always remember that it is between a hydrogen atom. The hydrogen bonding takes place between a hydrogen atom which is already bonded to a nitrogen, an oxygen, or a fluorine atom, and then that hydrogen atom will be in attraction with another nitrogen, an oxygen, or a fluorine atom. I will give you some examples to understand better what I'm trying to say. Here we have a hydrogen atom, and our hydrogen atom is already connected to oxygen. So because this hydrogen atom is already connected to the oxygen atom, then it can undergo hydrogen bonding with another oxygen atom. But if I have a substance like CH4, we have hydrogen here, we have another hydrogen here, and other hydrogen, and another one here. The hydrogen we have here cannot form hydrogen bonding with this one, with this oxygen. Why? Because the hydrogen we have here is not connected, already connected to oxygen, nitrogen, or fluorine. So all hydrogen atoms are not suitable for making hydrogen bonding. The only hydrogen atoms which can make hydrogen bonding, they are those ones which are already attached to one of these atoms, nitrogen, oxygen, or fluorine. If a hydrogen atom is not already connected to one of these ones, it cannot undergo hydrogen bonding. Let's have another example here. In a substance like CH3CHO, this is ethanol, an organic compound, there is no hydrogen bonding even if we have hydrogen and oxygen. Why can't we have hydrogen bonding in this compound? It is because this hydrogen we have here and the hydrogen atoms we have here, there is no one which is already connected to this oxygen, so we don't have any hydrogen which can be involved in hydrogen bonding formation. The increasing order of hydrogen bonding strength is nitrogen and hydrogen. They form the weakest hydrogen bonding because nitrogen is the one with the smallest electronegativity value, followed by oxygen and hydrogen, and the strongest hydrogen bonding will occur between fluorine and hydrogen because fluorine is the most electronegative element. Now let's go to the checkpoint. Identify the type of intermolecular forces present in the following substances. Here you pause the video and you will go on when you are done. We will have the answers at the end of our lesson today. Effects of hydrogen bonding on physical properties of compounds. Compounds which contain hydrogen bonding have unexpectedly high melting and boiling points. We have the example of water. Water has a boiling point of 100 Celsius degrees. But other substances which are even heavier than water, they are gases at room temperature. We can take the example of hydrogen sulfide. Hydrogen sulfide is heavier than water, but it is a gas at room temperature, showing that it has a low boiling point. So water has a very high melting and boiling point simply because it contains very strong intermolecular forces. The hydrogen bonding has so strong intermolecular forces that it requires a lot of energy to weaken them. They are also highly viscous, and here we can give the example of glycerol or the glycerin, the commercial name. Glycerin, you know, this substance which is used in cosmetic products. You know how viscous it is. So as the number of, or as the magnitude of hydrogen bonding increases in a substance, then it becomes more and more viscous. These compounds may be simple covalent substances which are solids at room temperature and pressure. We know the example of glucose. Glucose is one of the substances which are solids at room temperature while having a simple covalent structure. And this is because of the very strong hydrogen bonding glucose contains. It contains a big number of hydrogen bonding in its structure so that it becomes solid at room temperature and pressure. But you know, it melts at a very low temperature, showing that even if we have strong intermolecular forces, but they are not as strong as intramolecular forces, and that is the reason why even if it is a solid at room temperature, it melts at a low temperature. These substances containing hydrogen bonding, they are somehow special in the fact that they dissolve in water. Why do they dissolve in water? Some of them, even if they are covalent substances, they dissolve in polar solvents such as water, such as ethanol. Why? Because they have similar intermolecular forces. We know that ethanol contains hydrogen bonding as well as water, and that is the reason why ethanol, as a covalent substance, it can dissolve in water, which is also a polar substance. Why? Because they have same type of intermolecular forces. Other substances like urea can dissolve in water. Why? Because of the intermolecular forces, the hydrogen bonding they can generate between the solvent molecules and the solute molecules. And another example is that of ammonia. Ammonia is also soluble in water because of the hydrogen bonding it forms when it dissolves, it mixes with water. Some special properties of water caused by the presence of hydrogen bonding. Because of hydrogen bonding, water has some special properties such as high melting and boiling point. We explained this. The high surface tension. You know, very small insects like mosquitoes, they can stand on the surface of water. Why? Because of high surface tension. Why? Because molecules are joined together by strong intermolecular forces, the hydrogen bonding. Ice is less dense than liquid water. Why is it like this? It's because when liquid water is freezing, because of the hydrogen bonding, the molecules cannot get so close like in other substances. And in that case, some empty spaces will be left between the molecules of water when they are forming ice. And because of those empty spaces which are formed, the volume of ice increases while its mass doesn't change. And we know that when volume increases while mass is not changing, then density will do what? Density will decrease. So that is the reason why ice is less dense than liquid water. So ice will always float on the surface of water. And this one has a very important biological use. It will be for your research. And this water also has high heat of fusion and vaporization. To vaporize or to fuse water, it requires a lot of latent heat of fusion or latent heat of vaporization. Now let us have a look at the van der Waals forces or the London dispersion forces. And here you have to remember that they are the weakest intermolecular forces. They exist between all types of molecules. And they are also considered as temporary dipole-dipole forces. Temporary dipole-dipole forces to mean that the ones we have discussed earlier, the dipole-dipole interactions, those ones are permanent dipole-dipole forces. Why? Because the dipoles are always there in the molecules. But in the London dispersion forces, we don't have permanent dipoles. We have dipoles which are formed as a result of permanent shifting of charges in non-polar molecules to form temporary dipoles. So if you have a molecule like this with evenly distributed charges, the charges which are evenly distributed, it is very possible that the charge may rearrange themselves to have this. You have negative and negative to this side, positive and positive to this side. And if it becomes like this, then the neighboring molecule will be forced to rearrange its molecules, and we get negative to this side, negative to this side, and the positive to the opposite side, and the positive to the opposite side. And as a result, the positive pole, temporary pole, and the negative temporary pole will generate some attraction forces, but which are weak. Here you have to understand that once the molecules will be separated, the charge will redistribute again to come back to the normal distribution of these charges. And that is the reason why we say these dipoles, they are not permanent, they are temporary. And that is the reason why they generate intermolecular forces which are weaker. Here we have a diagram showing how two neighboring non-polar substances can approach each other and then generate an induced dipole-dipole attraction. Here we don't have poles. We don't have poles in this part, but in the next part we have poles. Negative, positive, negative, positive, and then these temporary dipoles, the positive and the negative, will be in attraction. Variation of van der Waals forces. What affects the magnitude of van der Waals forces? As the number of electrons in a molecule, and when the number of electrons is increasing, it means that the size is also increases. But here we can have some exceptions. But generally, when the number of electrons is increasing in a molecule or when the size is increasing, the van der Waals forces become stronger because we have so many electrons which will be involved in the shifting, in the temporary shifting, then resulting into temporary dipoles which are much stronger than when the size or when the number of electrons is small. And the melting and boiling points of the halogens, this is an example, increase down the group as the size and the number of electrons increases, hence making van der Waals forces stronger. As you move down the group from fluorine to chlorine, fluorine has 9 electrons, chlorine has 18 electrons, bromine has 35 electrons, while iodine has 53 electrons. So as the number of electrons is increasing, what happens? The van der Waals forces become stronger, and as they become stronger, then it makes the melting and boiling points of halogens increase. That is the reason why fluorine is a gas and chlorine is also a gas, but with a higher melting point and boiling point, while bromine is a liquid at room temperature and iodine a solid at room temperature. And this shows how the melting and boiling points of these substances is increasing as you go down the group. When we consider an example when one moves across a period, we can take that of sulfur, which has a higher melting point than phosphorus, and this is because of sulfur having a larger molecule than phosphorus. Sulfur has a molecule which contains 8 atoms, while phosphorus has a molecule which contains 4 atoms per molecule. So sulfur has a bigger size and more stronger intermolecular forces, the van der Waals forces, than phosphorus. Exercise. What kind of intermolecular forces are present in the substances below? Explain why ice floats on the surface of liquid water. Draw 2 molecules of water joined by hydrogen bonding, and ammonia has a higher boiling point than phosphine. The structure of phosphine, the molecular formula of phosphine is this one, and yet phosphine has a larger size than ammonia. Explain this observation. You will try the exercise and we will come back to correct the exercise and answer the questions you will encounter when watching the video. Thank you very much and have a nice day. See you soon.